Hello everyone. My name is Kuralamuthan Veerapandiyan. I'm a PhD scholar from IIT Madras, India. So this presentation is basically on the implementation of planetary motion for specified boundaries in a moving dynamic mesh. So the particular case that I have considered for this tutorial is a mixer, planetary mixer with a planetary blade and a central blade, which has a peculiar motion. The planetary blade undergoes two separate motions. One is the revolution about its own axis and a planetary gyration around the central axis as well. And the planetary motion undergoes a regular rotational motion. The issue arises during this simulation is this thin dynamic gap. So this thin dynamic gap moves in space and time as the simulation continues. It's not stationary, and that forms the basic crux of this tutorial case. So the already available methods such as mesh morphing, AMS sliding, overset, and rigid body motions cannot handle such a complex motion, as they have certain pitfalls in their own implementation, such as cell collapse, negative cell volumes, assume stationary gap in case of a sliding or AMI methodology, and overset requires a buffer cell to set the boundaries between the background mesh and the moving mesh, which is not possible in this particular case, as this dynamic thin gap varies as time progresses, and rigid body motion can't handle relative motion between those mixer blades. So the methodology that we developed here for this tutorial is includes coding utilities, coding boundary conditions, and then writing bash scripts to envelop everything into one seamless operation. So which I'll be explaining in a short bit. So we call this as a segmentation strategy. What we do is we have STL pre-processing utilities, we have mesh generation, and we have simulation broken up into segments. These are not continuous simulations from start to end, but the entire simulation is broken up into individual segments of specific delta t durations. STL pre-processing consists of two utilities implementation. One is STL to points and points to STL. These operate on STL files we supply to the Snappy XMesh. The STL to points utility will convert the trisurface STL files into vertices and store them into a text file. And points to STL utility will apply the transformations that we want in this case, the planetary motion and the rotational motion of the blades, and then reconstruct the STL into reconstruct the text files into STLs. Mesh generation will employ block mesh and snappy XMesh for each time segments. Like I have broken the entire simulation into 400 segments. The real-time value for the simulation is 4 seconds. I have broken it into 400 segments, and each segment will have a separate mesh generation using block mesh and snappy XMesh. A freshly generated mesh will have around 37,000 to 38,000 cells. And automatic local refinement is achieved through Snappy XMesh refinement properties. Like simulation is done through pimple foam with custom boundary conditions, and the custom boundary conditions drive the controlled mesh motion. And when one segment completes, we map the fields from the previous segment to the next new mesh, and we start the simulation fresh. So each 400 segment is a separate simulation on its own. On the whole, they will give us the complete simulation of the uh, entire tutorial. So this is the three pillars of our implementation. One is STL pre-processing, and then the custom boundary conditions and automation through bash scripts. So we already have certain dynamic mesh methodologies implemented in OpenFOAM. Those are mesh morphing techniques, rigid body motions, topology changing, and segmentation. Segmentation is our approach that we have developed for this particular case. And we will be using dynamic FE motion solver libraries with motion diffusivity being controlled in the dynamic mesh dictionary file. So the peculiarities for this particular case is the thin gap is a very thin gap of 3 to 4 mm. And the challenge is local mesh distortion as the simulation progresses and the gap moves around the domain continuously. It is not fixed and it does not oscillate about a mean position. It moves around continuously. And the resolution near the walls have to be very precise to resolve the viscous boundary layer effects. And the solver stability has to be maintained as skewed or non-orthogonal cells will cause divergence. So our solution for this particular case is decompose the entire simulation into steps, regenerate mesh at each segmentation step as to rectify the deformations caused due to the mesh motion and map the flow fields from previous segment to the new segment. So I'll share the terminal right now to explain what I'm trying to say. So when we move into the case setup, so we have a set of simulation folders that we have. One is case resources, which contains all the basic resources for running this particular case. Second one is the case snappy. Third is case extrude. Fourth is case mesh and case pimple and case results. In these available folders, case meshes and case results will contain the segmented values, the segmented time step details. Case meshes will contain all the poly meshes for particular time steps, and case results will have all the results that we have generated from this particular case. And we have all clean, all run mesh, all run sim. So the meshing has been broken into a separate subroutine through this all run mesh script, and the simulation has been broken into a separate subroutine through all run sim bash script. So we can run simultaneously both meshing and simulation. Just note that the meshing has to be done prior to running the simulation for that particular time step. If you are running segment 3 for mesh simulation, you should have the mesh generated priorly before running that simulation. Without that, we can run both. With that, we can run both the meshing and simulation parallelly, and this saves so much of time for our particular case. So the STL2 points and points to STL utilities will work on the STL files that we are supplying to Snappy Hex Mesh, and the custom boundary conditions that utilize this formula will move the mesh according to the angular velocity we have given as input to the simulation case. So the STL2 points utility will read each line from the STL library and write it as a text file with all the points vertices as a points file. And we apply the transformation to that STL using the solids disk file available in the case directory. So we'll be giving the number of points in that particular file, number of the translation that we want to provide in case of a planetary blade. Center blade doesn't have the translation, but planetary blade does have translation, and the angle at which the angle to which that particular boundary rotates during that particular segment, that will be provided through the solids data. So points to STL file will read the solid file, and that it applies a transformation to those points and then write it back into a STL file that can be used through SnapX Mesh. So the meshing workflow goes as follows. We broke the entire simulation into steps. We generate the background mesh with a rough mesh of around block size of 10 with 100 cells base mesh, and we run SnapX Mesh in 3 stages. One is cancellation, next one is snapping, and the third one is layer addition. Snapping and layer addition can be combined into a single step, but cancellation and other steps cannot be combined. We face some particular issues while running all three simultaneously. So we have broken that into 2 steps, and we perform quality checks initially to assess the delta t for a particular time segment. In this particular case that we have provided, the delta t for this particular case is 0.017 seconds, after which the mesh undergoes deformation and we don't have a good mesh quality to continue the simulation further. So we have fixed the delta t for our case as 0.001 seconds, 0.01 seconds. So every 0.01 seconds, the simulation stops. We generate a new mesh at that particular time step. We copy the fields from the previous step to the new step, and we start the simulation afresh from that new generated mesh, like that the mesh where we have copied our flow fields into. And the output of this particular case has around 37 to 38,000 cells per segment. This is a coarse mesh, and we have not validated the results yet. Um, I have explained this, so I'll go to the next one. So angular displacement, so the angular displacement is a custom boundary condition we imply to the central blade. So it takes in inputs like axis, origin, angle, omega, and point fields. So we have to define the number of points, the angle to which it is rotating. So when we run the simulation, this angular displacement source code class will take care of the mesh displacement that is being imparted into the central blade. Um, I have implemented this operator condition from the Rodriguez rotation formula, which I have got from CFD online forum. But this can be implemented using OpenFOAM's um, built-in code as well, so which is a part of the further development. So meshing, we have written as all run mesh. We have written a bash script called all run mesh. It takes care of all the meshing at particular time steps, and the core logic is being presented here in this page. We calculate the angle, we update the solid stick, we run STL to points, then points to STL. We run the snappy hex mesh, and we run extrude and layer addition. Once that has been done, we move the meshes to the case meshes directory with the correct time step that is being uh, meshed at that particular time. So once we have done that, we update the progress tracker, we update it to the case parameters bash script, and the simulation continues after this meshing happens. So case parameters file, I'll share it in the terminal. It will be much easier to understand. So this is the case parameters file. It contains all the simulation parameters that we are currently using. The omega center is the angular velocity of the central agitator. Omega planet is the angular velocity of the planet, and omega carrier is the angular velocity of the carrier. And the radial position of the planetary axis from the center of the mixer is 0.06 units. So the delta t that we are running for this particular simulation is e minus 5, and the end time for each segment is 0.01 seconds. And we'll be running the decomposition on, we'll be running the meshing and simulation on 4 processors. And the block mesh size can be controlled, block size, background mesh size can be controlled from this block size variable. And we'll be tracking the progress through these two variables, II and JJ. II tracks the variable for the mesh that's being generated, like the number of meshes that is being currently generated, and JJ tracks the simulation count. And the total number of meshing and simulation that we want to run for a particular simulation can be controlled using these two variables, n meshes and n sim. So, and we do have a bunch of helper functions, and these help us calculate the angular velocity, angle calculation for our particular boundary when running the meshing and simulation. So, for a particular time step, the all run mesh and all run sim will call this particular function to calculate the position to which the mesh has to be moved. And this status update function will update this II and JJ as both meshing and simulation progresses. And we have a bunch of form dictionary helper functions to update our dictionary files in the case directory. So updating them manually will be a huge task to remember everything where to do. So we have developed, we have coded certain helper functions to update those as well. So when we open the all run mesh, the core logic of all run happens within this while loop. So the while loop starts at 0 and runs till the number of meshes that you want to generate. As explained earlier, it goes through each steps one by one, updating the dictionary files, followed by running snappy xmesh in two different directories, one in case snappy and another one in case extrude. Once we have generated the mesh, we'll get the results in the meshes directory. So you can see from this paraview uh, paraviews window that we have generated a mesh with refinements in regions where we have uh, regions of interest. So you can see from this particular window that we have added inflation layers of around 10, I suppose if I'm not wrong, 10 inflation layers around all the moving boundaries and the outer wall as well. And the regions where the bulk of the fluid is not undergoing particular motion is not refined to that extent. We can change this. This is a coarse mesh, so we have a coarser distribution of this particular region. But when we run a fine mesh, we hope we'll get good results. So the flow of the simulation is like we'll update the point displacement to include the omega. We'll compute the velocity from the point displacement. We'll update the dictionary files in the simulation directory, followed by pimple form running the solver, and we'll get the results from that. So to run the tutorial, we'll just set the case parameters like number of meshes we want to generate, the delta t that we are interested in, and we run all run mesh, all run sim, and we'll post process the results using uh, paraform or paraview in case. So customization, when we want to run this particular solver or particular implementation for a new uh, mixer case, we just replace the mixer.stl in our case snappy. So we do have a mixer.stl in this particular directory. When we change this mixer.stl to include all the different boundaries or different geometry that we want to simulate, we can get meshes for those particular geometry as well. So when we run the simulations and when we run the paraview animation for this particular case, we get good results which are yet to be validated. And when I plot the cell displacement with this particular case, we can see the displacement around this both the central agitator and the planetary agitator, planetary blade, and the maximum cell displacement is concentrated around this planetary blade. So when we zoom in, we can see the mesh motion that's being generated. Uh, so the particular issue with this sort of case is as the simulation progresses, we can see the cells are being distorted. And the cells tend to have abnormal aspect ratio or concave structures or negative volumes, which seriously affect the simulation and the solution diverges. So this particular implementation will help us in avoiding that issue by interpolating this result. This is for one particular segment from 0 seconds to um, zero point zero 0.01 seconds. Once the simulation ran till 0.01 seconds, we stop the simulation. We take these fields and interpolate onto the mesh, and then we get the output for that for the next segment. We can run the case for different solvers, and we can run for a course study. But I might warn you that reducing the mesh size below a block size of 10 to not mesh around this particular thin gap regions, which are neglected when the base mesh is too coarse to run. So block size of 10 is the least possible mesh size that I was able to run this particular implementation. And the mesh quality analysis yields us a cell count of 35,000 to 38,000 cells and non-orthogonality with a maximum of 65. Skewness of 0.85 and expansion ratio for the inflation layers as 1.2, which is a smooth transition. As I have discussed earlier, after 0.017 seconds, the mesh tend to deform too much. We cannot use this particular mesh after 0.017 seconds. Flow field characteristics. When we ran the simulations, we got high recirculation region, strong vortex between the blades and the vessel wall, thin gap shear and extreme high velocity gradients between the blades. Pressure distribution is high on the leading phase and low on the wake, and there is a periodic mixing pattern for the planetary blade as well. Um, like visualizing using paraview with the point displacement field will gives us the idea on where we have the maximum displacement, which is concentrated around the planetary blades. So the computational cost for this particular case is listed in this table. Like STL to points and points to STL takes the minimum time, since it's just manipulating the STL files through matrix transformation. So the castellated mesh takes around 45 seconds per segment. This computational scaling is for 20 cores, but if you run in 4 cores, your time will be vastly different. Snapping and layers takes around 15 seconds, and pimple foam is the maximum dominant computational cost with around 110 seconds for a particular segment, and maps field power will take 10 seconds. So essentially for 400 segments, and 20 cores, I have to run the simulation for around 20 hours to get the entire simulation output. With pre-processing doesn't account for much of the simulation time, with simulation occupying more than half of what we spent on calculating. So we have residuals. These are not verified residuals, but these gave us working values for our particular case with continuity residuals 10 E minus 6, velocity residuals E minus 6, and pressure residuals as E minus 5 with two outer characters and two pressure characters. Map fields par uses cell volume weight interpolation, and mapping error is less than 1% for smooth fields. Future implementation will be to implement generalized 3D rotation with translation with 6 degrees of freedom. Time dependent variation with acceleration deceleration can be implemented, and adaptive meshing can be implemented to refine near the regions where we have high shear. Turbulence is not yet considered in this case. I have ran the simulation for laminar case alone. Turbulence can be considered for a future improvement, and multi-phase flow can be implemented. And this application um, can be extended to other simulation cases like planetary gearboxes, piston cylinder arrangement, pump impellers, and valve seats as well. So key takeaway is that segmentation is a good alternative to existing methodologies to run simulations on uh, certain mechanical instruments where we see a dynamic boundary which is not oscillating about a mean position. And the automation is critical in this particular case as we are handling 400 plus simulations in this particular case alone. Automating them using bash script is a good idea. Custom boundary conditions are embedded into the OpenFOAM's source code itself. And field mapping works flawlessly. Like we initially ran map fields par in a serial arrangement, and then we converted it into parallel arrangement. Like parallel gave us a speed up of around 7 to 8 times. So if we are running map fields par in parallel, in serial, it is a very bad choice to run it. And the code availability, I have added all the codes that I have developed into the uh, accompanying files that I have submitted. The summary is that we have implemented a simulation strategy to simulate dynamic thin gaps, which is a segmentation strategy. We have STL preprocessing, custom boundary conditions, automation using bash scripts. This particular framework can be used to simulate any other sort of moving boundary conditions as well. It's extendable. So the methodology is robust and reproducible and reusable. So learning outcomes, it's like we can configure the case parameters and all-run mesh and all-run sim with new boundary conditions as well to run particular simulation cases. We are not using any previously implemented methodologies like morphing AMI or overset. We have implemented a new methodology to mitigate this issue of dynamic thin gap, and C++ boundary conditions with Rodriguez rotation formula we have implemented, and dynamic FE meshes and motion solver libraries are used to implement this particular methodology. And to modify it, we can change the we can change the geometry by changing the mixer.stl file, and we can extend this we can extend this implementation by implementing transformation matrices and generalized bash script for different cases. I guess I'm I'm completing my presentation right now. If you have any questions, I'm open to it.